I'm Jeff Groh, and this is Calculus 1. Today we're going to talk about an integration method called the method of substitution. Or I would just like to call it sometimes U-subs. The method is based on reversing the chain rule. So let's just review the chain rule. If you take the derivative of a composition f composed with g, you should take the derivative of the outside function and leave the inside function alone, and then multiply by the derivative of the inside function. It follows then that if we integrate this derivative, since the integral is the class of antiderivatives, and an antiderivative of a derivative is just the original function to within a constant, we get f of g of x plus c. It follows then that f of g of x plus c is the integral of f prime of g of x times g prime of x dx. This is where we're going to use this dx. It suggests the following method. We'll set u equal to the inside function that has its derivative lying around. It follows as a consequence from our knowledge of differentials that du is g prime of x dx. These are all side computations. The original integral transforms as follows. U is going to replace g of x, so we're going to have f prime of u. G prime of x dx is replaced by du. Now we know that the integral of the derivative cancels out, so this is going to be f of u plus a constant, and we already know that u is g of x, so that this is f of g of x plus c. This shows how this method works. Let's try this out. As a simple example, let's suppose that we're integrating x squared plus 5 to the power of, say, 11 times 2x dx. As you can see, we have the derivative of something lying around. We have an inside function, and we have the outside function, which is the power 11. The derivative of the inside function is just lying around, multiplied onto the dx. That suggests we should make u equal to the thing that has its derivative lying around, x squared plus 5 in this case. Du would be 2x dx. That means the integral transforms into u to the power 11 times du. We now know how to calculate the remaining integral using the power rule for antiderivatives. That's u to the 12 over 12 plus c. At this point, we're not done. We still have to substitute back. The original problem had nothing to do with u, and so we need to replace u with what u equals. So we'll have 1/12 x squared plus 5 to the power 12 plus c, and that is the answer. Let's try this again. Suppose that I'm integrating 3x squared times the square root of x cubed plus 5. What should you choose for u? u is the thing that has its derivative lying around. So u is x cubed plus 5. Yes, make sure you include that plus 5 as part of the u. Du is then 3x squared dx. The integral is now transformed. It transforms as u to the power of 1/2, or the square root of u, and then the 3x squared dx goes away to become du. You need to know what happened to every single term in this expression. We have then u to the power of 3/2 times 2/3 plus an arbitrary constant of integration. Substituting back, we have 2/3 times the quantity x cubed plus 5 to the power of 3/2 plus an arbitrary constant c. Suppose that we're integrating cosine to the power of 5th of x sine of x dx. As you can see, the derivative of cosine is not sine, but minus sine. But that's okay. We can take care of those constant factors. We'll make u equal to the thing that has its derivative lying around. Cosine x, not cosine to the 5th x, just cosine x. Du is going to be minus sine x dx. We have sine x dx, but not this minus. So I'm going to multiply both sides by a minus 1. I'll replace sine x dx by a negative du. This negative can come out of the integral. Make sure that you understand what just happened here. Finding the antiderivative using the power rule is now an easy step. Negative u to the 6th over 6 plus c. And then substituting back, we have negative 1/6 cosine to the 6th of x plus c. Let me give you another example where we have to fix one of the constants. Let's suppose I'm integrating u cubed times x to the 4th plus 1 to the power of, let's say, 2/5. We don't exactly have the derivative of something lying around, but we do almost, in the sense of there's a constant factor missing. Nonetheless, we can always fudge those common factors. We'll set u equal to x to the 4th plus 1, so that du is 4x cubed dx. Make sure you write these dx's and du's and you're very careful about tracking these differentials. They're important. If you abuse this notation, it will abuse you back. We don't need this 4, so we're going to divide it off. This factor of 1/4 can come out in front of the integral. And we'll end up with 1/4 the integral of u to the power 2/5 du. We now apply the power rule for anti-differentiation. We have this 1/4, I'm going to leave a little gap, u to the power of, well, I need to add 1 to the exponent. That gives me 7/5. And when we divide by 7/5, it's like multiplying by 5/7. So we're going to have 5/28 out front, followed by x to the 4th plus 1 to the power of 7/5 plus an arbitrary constant of integration. Sometimes u is the thing that has its derivative lying around. At other times, u is kind of the impediment, as you shall see. Suppose I'm integrating the square root of 2x minus 1. If this were just the square root of x, I could use the power rule. Well, let's make it so. U is 2x minus 1. By the way, I get a kick out of saying U is, because this is the one context in which that grammatical construct is correct. Du is 2 dx. We don't have the 2, so we're going to divide it to the other side. I'm going to encapsulate all of this substitution information inside of a box, because that's a side calculation. We're going to get 1/2 the integral of u to the 1/2 du. This gives us this 1/2, leaving a gap, u to the 3/2. When we divide by 3/2, that's multiplying by 2/3 plus c. Our answer is 1/3 times the quantity 2x minus 1 to the power of 3/2 plus c. Suppose I have the integral of e to the 2x dx. 2x, this 2 right here, is the impediment. So I'm going to make u equal to this entire exponent, 2x, so that I can integrate e to the u. That should be no problem. What is the price I have to pay? Du is going to be 2 dx. To replace just dx, I need to divide the 2 off. And the integral is transformed as 1/2 the integral of e to the u du. Well, that's easy. The integral of e to the u is e to the u plus c, and then substituting back, we'll have 1/2 e to the 2x plus c. I want you to carefully consider this particular example. More generally, if I'm integrating e to the ax, you should be able to pretty easily see that I'll have 1 over a e to the ax plus c. Remember, if we take the derivative of e to the ax by the chain rule, we get a e to the ax. When we integrate, we get 1 over a e to the ax plus c. Similarly, if I'm integrating, let's say, cosine of 3x dx, there's a substitution u equals 3x, so that du is 3 dx. Only having the dx, we divide the 3 off and get 1/3 the integral of cosine of u du. The antiderivative then is clearly 1/3 sine of u plus c, or 1/3 sine of 3x plus c. Notice how, reversing the chain rule, you end up dividing by the derivative of the inside, not multiplying. Suppose that I'm integrating x square root of 3x plus 4. The impediment now is 3x plus 4. We don't really see the derivative of anything lying around. So we'll make u equal to the impediment. du is then 3 dx, and we'll divide this 3 off. But we need to do one more thing before we go on. We need to figure out how to replace x with something involving u. To do that, we'll solve for x here. We'll move the 4 over, and then divide the 3 off. These are all part of the side computation. The integral becomes, we get dx replaced by 1/3 du. X is replaced by u minus 4 divided by 3, and 3x plus 4 is replaced by u. Make sure you know where everything went here. This 3 in the first factor of the integrand can come out, joining the 3 outside of the integral, leaving 1/9. We'll distribute the u to the 1/2 on each of the two terms inside of the parentheses. That'll give us u to the 3/2 minus 4 u to the 1/2, all times du. The parentheses in this case are considered to be optional because it's assumed that du is multiplying the entire integrand. Calculating the integral now using the power rule for antiderivatives. We have 1/9 u to the 5/2 times 2/5 minus 4 times, here we'll have u to the 3/2 times 2/3 plus c. Substituting back for u, we'll have 2/45 times 3x plus 4 to the power of 5/2 minus 8/27 times the quantity 3x plus 4 to the power of 3/2 plus c. Suppose I'm integrating the sine of the square root of x divided by the square root of x. What is u? U is the square root of x. That's the impediment, and it has its derivative more or less lying around. Du is 1/2 root x dx. We have the dx divided by square root of x. What's missing is the 2 in the denominator, so we're going to multiply both sides of this by 2. I'll encapsulate this as a little side computation. We end up with twice the integral of the sine of u du. Make sure that you know where everything went. The integral of sine is minus cosine. So we have minus 2 cosine of u plus c. Substituting back for u, we have minus 2 cosine of the square root of x plus c. How does substitution work when we have limits of integration? Let's suppose that we're integrating from 1 to 3 of, let's say, 2x square root of x squared plus 4 dx. The u substitution is going to be x squared plus 4, and du will be 2x dx. Seems simple enough. The integral is transformed as the integral of u to the 1/2 du, but what about the limits of integration? These are x limits. X goes from 1 to 3. If x is 1, substituting x equals 1 for u, in our substitution we have u is equal to 5. Similarly, if x is equal to 3, 3 squared is 9, plus 4 is 13. It follows then that we have u to the 3 halves times 2 thirds evaluated from 5 to 13. Recall that if I have a number to the power of 3 halves, that's the same number to the power of 1 plus a half, which is that number times the square root of that number. It follows then that we have 2 thirds times 13 times the square root of 13 minus 5 times the square root of 5. No plus c's on definite integrals. I'd like to talk for a minute about even and odd functions. What is an odd function? A function that does inappropriate things in social settings? That's not an odd function. No. A function f is called odd if f of negative x is negative f of x. It is even if f of negative x is positive f of x. Why should these be the definitions for even and odd functions? Consider the function f of x equals x cubed. Notice that the exponent here is odd. F of negative x is negative x cubed, which means we get 3 factors of minus 1. That reduces to just minus x cubed. Notice that by the order of operations agreement, the cube here only applies to the x and not to the minus, so we only have one minus sign now. And that is the negative of the original function. It follows that x cubed is odd. Go figure. Similarly, the function x squared is even. F of minus x is minus x squared. The negative gets squared away, and we end up with f of x. Therefore, f of x equals x squared is even. Every function may be decomposed into the sum of even and odd parts. We can call that a theorem. If f is mapping some interval from negative a to a into the real numbers, then there exists an even function h of x and an odd function g of x, such that f of x is an odd part plus an even part. The proof of this theorem is just as important as the statement, because you need to know how to perform this construction. So the proof goes like this. Set h of x to be f of x plus f of minus x divided by 2. That will be the even part. And g of x equal f of x minus f of minus x over 2. it's pretty easy to see that f of x will in fact be g of x plus h of x. We have a 1/2 of f of x added to a 1/2 of f of x. Gives us all of an f of x when we add these two. And the f of minus x's will cancel out because they have coefficients having opposite signs. What's left to prove is that h is even and g is odd. To see that h is even, we apply the definition for an even function. We'll replace x by negative x everywhere in sight. Minus a negative is a positive, and addition is commutative, so I can rewrite the numerator on the right-hand side as f of x plus f of minus x over 2, but that is the original definition of h of x. So for h of x, the negative goes away when you substitute negative x for x. Similarly, g of negative x is f of negative x minus f of minus negative x over 2. Minus minus is positive. When you reverse the order of a subtraction, you end up with a minus sign. And so we get the negative of g of x, and therefore g is odd. That's the end of the theorem. If a function is even, then its odd part will be identically 0. And if it is odd, then its even part will be identically 0. Even functions, because they satisfy the equation f of negative x equals f of x, will be symmetric about the y-axis. At x and negative x, they will have the same height. Odd functions, because they satisfy f of negative x equals negative f of x, have symmetry through the origin. Whatever happens at x, you get the opposite at negative x. That means if you integrate an odd function from minus a to a, you must get 0. For example, suppose I'm integrating from negative 1 to 1 x times the square root of x squared plus 3. I claim that the integrand is odd, and since we're integrating from negative 1 to 1, the answer is 0. Normally, I would require no further evidence for this. Set f of x to be x times the square root of x squared plus 3. How do I know that this function is odd? After you see this example, you'll be able to do these in your head. We replace x by negative x everywhere in sight. Inside of the square root, the negative gets squared away, and in front, we just have a negative that dangles out all by its lonesome. We end up with the negative of the function that we started with. Therefore, f is odd. That means this integral is 0, just by symmetry. Do you see the power of this idea of dealing with even functions and odd functions? It can greatly simplify the solution process. You might recall that the sine function is odd. Whatever happens at x, you get the opposite at negative x. It follows that if you were to integrate from negative pi over 2 to pi over 2 the function sine of x, you would get 0, just because sine is odd and you're integrating from negative a to a. You need to say nothing more. Let me give you another example. Suppose I'm integrating from negative pi over 2 to pi over 2 of sine of x times cosine of x. Is the integrand even, odd, or neither? It turns out that if my function is the product sine of x, which is odd, and cosine of x, which is even, then what happens with f of minus x? On the sine, a negative comes out, and on the cosine, the negative disappears, which means I get the negative of the original function. That means this function, sine x times cosine of x, is odd. If you multiply an odd function and an even function, a negative will come out of the odd and disappear from the even. It follows that you get one negative out front, and hence, anytime you multiply an odd function times an even function, you end up with an odd function. Notice that's not true for odd and even numbers. It's true for odd and even functions. It follows then that this integral is 0. No further computation is required. Things are not quite as simple for even functions, but almost. There are some advantages you can take. For an even function, if you're integrating from negative a to a, you may as well integrate from 0 to a and multiply by 2. So if f is even, you may as well do the following. Do twice the integral from 0 to a. There are going to be certain advantages to that. Let's do the simplest possible example. And let's do this two ways. First, just apply the fundamental theorem of calculus. We'll have 1/3 minus negative 1 cubed over 3. This minus will cancel this. We'll have 1/3 plus 1/3, and we get an answer of 2/3. The problem with this last computation is that students often mess up the minus sign. This should be twice the integral from 0 to 1. Applying the power rule, we get twice x cubed over 3 evaluated from 0 to 1. Plugging in the 1, we get 2/3, and then we subtract plugging in 0, which is 0. So the answer is 2/3. There's less chance for error here because we don't have to subtract a negative. We know the following theorem is true. If f is odd, then the integral from negative a to a of f of x is 0. This is an implication in one direction, but it leaves open the question, does the implication go in the other direction as well? If you get the integral from negative a to a to be 0 for all a, does that imply that f is odd? I'm going to state this as a theorem. If the integral from negative x to x of f of t dt is 0 for all x, then f is odd. Let's prove this. Let big F be an antiderivative of little f. By the second fundamental theorem of calculus, the integral from negative x to x of f of t dt will be big F of x minus big F of minus x. And by hypothesis in the theorem, we get 0 when we integrate from negative x to x. Taking the derivative of each side, we have 0. The derivative of big F is little f. Over here we need to apply the chain rule. The derivative of big F is little f, leave the inside alone, but then you have to multiply by the derivative of the inside, which is -1. This negative is inside of little f. This negative can cancel the negative here. Moving this term to the other side, we deduce then that f of negative x is negative f of x. Therefore, f is odd. And that is the end of the proof.